Once you have determined the equilibrium constant K for a reaction, we can use that to calculate concentrations of substance in equilibrium mixtures. So if we know K and we know several of the equilibrium concentrations, we can solve for the one that we're missing. Okay, so this is the simplest calculation. Then we'll move on to actually calculating equilibrium concentrations of all the species. So let's look at this example. Considering the following equilibrium mixture, carbon monoxide, hydrogen plus gives me methane and water. Suppose a gaseous mixture containing 0.3 moles of carbon monoxide, 0.1 moles of hydrogen, 0.02 moles of water, and an unknown amount of methane per liter at equilibrium. What is the concentration of methane at equilibrium in this mixture? The equilibrium constant Kc is 3.92. The thing to realize in this particular problem, which is different from what we're going to do in the next problem, is that this is an equilibrium mixture. Okay, so this is telling me the amount of these values are my equilibrium amounts. Okay, if that's the case, then all I gotta do is plug it into the Kc, solve for the one that's missing, and get my answer. Plug and chug problem. If it said this was the initial concentrations, I can't do that. I can't just solve for the one missing. I'm going to have to do my ice table and solve for the equilibrium concentrations through that Kc value. Okay, so the reason that we can do this problem simply is because of the fact that it says these are equilibrium mixtures. That's a key word in determining how I'm going to work this problem. This is just a simple plug and chug problem because I'm at equilibrium. So you have to determine your concentrations, which is moles over volume. This is straightforward since it's 1 liter, but 0.3 over 1 is 0.3 molarity, 0.1 over 1, 0.1 molarity, 0.02 over 1 is 0.02 molarity, and then we're trying to find that concentration of methane. These are all equilibrium values, okay? These are all equilibrium values because that's the way it was given in this problem. The K would be your methane to the first, water to the first, divided by carbon monoxide to the first, divided by hydrogen to the third. Okay? So these are equilibrium values, so I'll just plug those in. I know Kc was given to me. The only thing that's missing is that methane is what we're looking for. So this is just a case of doing a little arithmetic and coming up with the final answer. So I'll plug those values in. I get my 0.02 for the water, my 0.3 for the carbon monoxide, the 0.1 cubed for the hydrogen. Now I got to do some arithmetic, which means I'm going to divide through by 0.02 on both sides and bring that 0.02 to the other side. I'll multiply through by my 0.3 on both sides. So that gives me my 0.3 times my 3.92. And multiply both sides by 0.1 to the third. That way I'm canceling out those units as well. Which gives me methane then is equal to 3.92 times 3.30 times 0.1 to the cube divided by 0.02. I do the math, I get 0.059. The one thing to keep in mind is as long as I'm plugging in molarities into my Kc, remember Kc is unitless. I don't need to put the molarities behind it because they're not going to cancel out. Okay, but I do have to remember I'm trying to solve for concentration here, so I'm going to have to remember to put molarity behind that numeric value that I'm calculating. In this case, our value is 0.09 moles per liter, or molarity, which is the concentration of the methane at equilibrium. As I said, pretty straightforward if it's equilibrium mixture. Okay, key there being an equilibrium mixture. Now, if I start off with initial concentrations, then I've got a little more detailed calculation, which we're going to show you in the next problem. Suppose we began a reaction with known amounts of starting material, and we want to know calculate the quantities at equilibrium. Okay, it may be a case that I start off with just my number of moles of reactants. Okay, or I could start off with just a number of moles of products and no reactants. Shift left or right, or I could have a little bit of everything, and I have to solve for Q and figure out which way things shift. All cases are still going to be the same. We're going to do our ice table and calculate for that X and then solve for those values. Remember, we did this a while back when I showed you that the K was the same whether I started with reactants or products. Remember, I started off a problem with reactants and I came up with some K value. Then I did the same equation, but I did it starting off with reactants and I came up with the same K. In that process, I said experimentally I determined the equilibrium concentrations of each species. Now, they were all different values, but the ratio still equals that K. What we're going to do now is show you how you could calculate those experimental numbers. You didn't have to go into the lab to get those numbers. You could have just calculated it with, if you knew K, you can calculate what the concentration of each species would be at equilibrium, following the next procedure that I'm going to show you. Example, I start off with 1 mole of carbon monoxide and water each, and it's in 50-liter container. Calculate the molarity of each substance in its equilibrium mixture at 1,000 degrees C. Also give you the Kc is 0.58 at 1,000 degrees C. Once again, the 1,000 degrees C only matters that we're doing the experiment at the same temperature of the Kc that we know. Okay, so I know the concentrations of my CO in the water. I'm going to have to calculate it, but it's 1 mole in 50 liters. There's no indication of any CO2 or H2, so that's 0 moles, okay, of each one of those. So one of the first things I'm going to have to think about when I put it into my ice table is which direction is this reaction going to go? Since I only have reactants and no products, which way is this going to have to shift to reach equilibrium? It's going to have to go to the right. Since it's going to the right, that means I'm going to do what? I'm going to be consuming up my CO and water, so it's going down in value, and my CO2 and H2 are going to increase in amount of substance. Now, if I started with products and no reactants, it'd be going the other direction. I'm going to have my signs opposite as well. If I had a little bit of everything, I would have to solve for Q to figure out which way it's going to put my minuses and pluses to be able to work the problem correctly. So next step, I want to figure out my molarities because everything's concentration based, so I need to do that. So 1 mole divided by 50 is 0.02. 1 mole divided by 50 is 0.02, 0 and 0. I'll now take these values and I will now set up my ice table to work up my problem. So my problem here is I'm trying to find the equilibrium expressions, okay, for all my species, okay, by writing in my ice table. Okay, what's the goal of this experiment? Okay, the goal of this experiment is to determine the concentration of all 4 of those components at equilibrium. Okay, remember we can write the K for this equation. CO plus water gives me CO2 and H2. It basically would be the concentration of my CO2 at equilibrium times the concentration of my H2 at equilibrium divided by my concentration of CO at equilibrium divided by my concentration of water at equilibrium. Okay. Well, right now I know Kc, but I do not know CO2, H2, CO, and water at equilibrium. So basically I have one equation and 4 unknowns, which is not solvable. I cannot solve one equation and 4 unknowns. So I'm going to have to find a way to manipulate this equation to get it to one equation and 1 unknown. So somehow I'm going to have to relate CO2, H2, CO, and water all within one variable if I want to solve this equation. That's where this ice table is going to come into play. So we set up our ice table. Once again, I got some initial, some change, and something at equilibrium. I was given my initial values of 0.02 for CO and 0.02 for water, and 0 for carbon dioxide and 0 for H2. My next thing is which way is this going to shift? We said that this is going to shift to the right, okay, which means then I'll have negative change in concentration for each of my CO and waters, and I will have positive changes for each of my H2s. Next question is how much change, how much CO is going to be consumed. So I'm going to go with the ratio of my coefficients. So I'm going to say X of it's going to be consumed in CO, X of it's going to be consumed in water, and how much CO2 is going to be produced, X, how much H2, X. So we have our change. So what do we have at equilibrium? Well, that's just adding your initials and your change, which then tell me I got 0.0200 minus X for carbon monoxide, 0.0200 minus X for water, X for carbon dioxide, and X for H2. Those are my answers. 0.2 minus X, 0.2 minus X, X, and X. That's what I'm looking for. That's my goal. However, I want this in some numeric value. I don't want it in terms of X. So the question is, how are these equilibrium values related? How are these things related that I can mathematically solve for that X? Well, they're related through Kc. So if I plug these into my equation now, I can take that X for hydrogen, plug it in, because that is my equilibrium value, take my X and plug it into CO2, plug my 0.02 minus X and plug it into water, and my 0.02 minus X and plug it into carbon monoxide. Now I have one equation and how many variables? One, just X. So now I can solve the math of that, solve for X, plug it into my expressions, and have my equilibrium concentrations. So if we substitute our values into those equations, I'll get X for hydrogen, X for carbon dioxide, 0.02 minus X for carbon monoxide, and 0.02 minus X for water. Now continuing on with the math, X times X is X squared, and 0.02 minus X would be squared as well. Now notice in this particular example that I got 0.02 and 0.02, the same numeric number. When you have the same number for your reactants, what's going to happen is you're going to end up with something called a perfect square, which means I have a square term over a squared term. If those numbers are not the same, reactant 1 and reactant 2 are different concentrations, most likely you won't have a perfect square, and you're going to have to solve that with a little bit more math, okay, compared to what we're going to do in this problem. Ultimately, either one case, this problem or any future problems, we could use something called the quadratic formula, okay, to solve our math. But sometimes we simplify the math because we get something called the perfect square, okay, which is what we have here. Okay, which is basically a square term over a square term. Okay, if that happens, then I can simplify the math and do it a little easier. However, if that's not a perfect square, then we have to use the quadratic formula, which will do a problem like that eventually. Okay, so what I can do, since it's a perfect square, is take the square root of both sides to simplify and get rid of that square term and simplify it in the sense that I can do my math a little easier. So I'll take the square root of both sides. When I take the square root of both sides, square root of my 0.58 gives me 0.76. The square root of my x squared now changes into just x. And the square root of my 0.02 minus x turns into just 0.02 minus x. And in other words, we eliminated the square term. So mathematically now I have to solve this. So now I'll take this expression and multiply it on the other side by multiplying through on both sides, which now gives me 0.76 times 0.0200 minus x equal to x. Then I got to multiply through by 0.76 to both terms, which is 0.76 times 0.0200, which gives me 0.0152, and 0.76 times a negative x gives me a negative 0.76x. Now I want to get x's together on the same side, so now I will add 0.76x to both sides. So my lose it on my one side. The other side, you got to remember I got a 1 in front of that x, so it's 1 plus 0.76, which gets me 1.76x equal to 0.0152. Divide through by both sides for my 176. Which gets me 0.0086 as x. Now we got to remember we're doing this on a concentration base, so I got to remember to put that unit of molarity on it. That gives me x. Now does that give me my final answer? The answer is no, because I want the equilibrium concentrations of each species, which are these expressions up here, 0.02 minus x and x. So how can I find my answer that I'm looking for? Well, that's just plug in those answers, that x value, into my X components, and I can solve for my answer. So substituting in, for the carbon monoxide, it's 0.02 minus X, so it's 0.02 minus 0.0086, which gets me 0.0114 molarity. Same expression for the water, it's 0.0200 minus X, which is 0.0200 minus 0.0086, which is 0.0114. Carbon dioxide would be just X, which is 0.0086, and hydrogen would be just X, which is 0.0086. These are my final answers. Ones are we looking for? Now, is there a way that I can check to see if I did my calculations correct? Yes. If you just plug these values back into your K expression, you should equal K. Now, granted, you got to remember, based on sig figs here, it's only going to be the answer is going to be the same up to your uncertainty. So if you have 2 sig figs, is what we have right here, okay, your uncertainty is going to be in that second digit. So this equation was, I think K was 0.58. You may calculate this using the numbers. You may get 0.56, 0.59. That last digit's your uncertain one. So as long as you equal to within that last certain uncertainty digit number, then you're okay. Okay, you got to remember, you got to count for that sig fig. And we don't have many sig figs here, so it can't be as accurate as one would think. Homework 19. Okay, thing to caution you about this homework, it's just like we just did here. It's all about reactants going to products, and I don't want you to get a false sense of security that it's always that way. Okay, got to remember, other questions are going to come and it's going to go the other way. You're going to have products going to reactants, which means that you're going to have to change the signs of your change. So don't get in the habit of always putting minuses on the left side and pluses on the right side. It depends on what the problem dictates. Okay. The homework right now, we only covered this one type of problem, so all of them are going to have that. So keep that in mind as you work them, because when you get to the tests, things are going to be mixed up. And you have to decide, is it minus or plus? It's not always minus on the left side and always plus on the right side. It could be the opposite. So make sure you're looking at the problem to decide which way is correct.